Good day, good morning, good evening in my case. Actually, good night. It's pretty much the middle of the night here in Australia. My name is Caroline Foster, and I'm the Astro 3D Research Fellow at the University of Sydney. I'm also one of the 4 PIs of the newly started Magpie Light program on the MUSE instrument. Today, I've been asked to give a review of stellar kinematics in external galaxies. It's going to be a very broad overview, not very deep, very shallow, because it's a huge field to cover. And hopefully, though, it will give people food for thought for discussion later on. I'm going to mainly focus on recent results and the current state of affairs, but I want to acknowledge that a lot of the groundwork for this was really laid out 6, 7 decades ago. And so, we are truly standing on the shoulders of giants. I'm also going to assume that contributed talks have been visioned already. And so I'll try to avoid repeating what's already been said in those talks. Right. So first of all, I wanted to put a little bit of context into this very broad topic. So I've got 2 slides of context coming. First of all, this is a schematic of a galaxy, so to speak, which may or may not have multiple components. So in this case, I've given it an inner component. You should maybe call it the bulge. And then an outer component could be the stellar halo or maybe a disk. And then this stellar ensemble is embedded within a dark matter halo, which is much, much larger in scale. And so even just the stellar component of galaxies for nearby galaxies can extend out to several arc minutes, which can be a technological challenge sometimes to reach out to the outskirts of these galaxies. But the outskirts of galaxies are also very interesting because this is where we can see the contribution of of stars that have been fallen from galaxies that have been accreted. And so basically, the field has been pushed by the different technological advances over the years, starting from just spectroscopy of the very centers of galaxies, and then moving on to long slit spectroscopy, which would allow for spatially resolved spectroscopy along a single axis, and then obviously integral field spectroscopy in the last 2 decades or so. To circumvent the problem of the very faint starlight in the outskirts of galaxies, certain techniques using bright dynamical traces have been developed to be able to extend and push out in the outskirts and understand the stellar kinematics over there. So I've made a little compilation, and it's not exhaustive, and I apologize if your favorite survey isn't represented on there, but I've tried my very best. And I've used the different technologies that I've discussed before, and I've used different symbols for each of those in this plot. And I've also scaled the sizes of the different symbols according to how far out they reach in galactocentric distance in effective radii. Also, I've color-coded them as a function of the highest redshift that the survey reaches. And finally, what was the other one? Yeah, that's it. Right. And so I've got on the y-axis the number of galaxies in the survey of stellar kinematics, and on the x-axis the year that the main paper or survey paper was published for that group. And we can see in general 3 trends in this plot. First of all, there's like a Moore's law kind of trend going on where over time we are having more and more larger and larger samples, which is good news. But also in parallel to that, we're seeing the symbols getting lighter, which means we're pushing out in redshifts. Obviously, nothing like what Federico was talking about before. We're still very much, at tops redshift of 1 for stellar kinematics still at this point. And then also pushing out into the outskirts of these galaxies. So very much trying to reach out further to try and understand the in situ versus accreted stellar dynamics. Right, so I've divided my talk into 2 parts, and I'm going to speed through a whole lot, so I apologize if it's a lot of information. But the first part is I'm going to talk about scaling relations and different ways that we've characterized the stellar dynamics or stellar kinematics in galaxies. So first of all, I'm going to revisit the Fabre-Jackson relation. And this is work by Srio and collaborators, and basically looking at the Fabre-Jackson basically defining it using galaxies that have a very high bulge to total ratios, shown here in orange, and the orange line is the fit to those. We can see that galaxies that have a lower bulge to total ratio tend to move away from this relationship. However, using stellar kinematic bulge disk decomposition, they were able to show that basically the bulges and disks lie on their own Faber-Jackson relation, if you like, that are parallel to each other, but with very, very similar slopes. Here I'm showing work by Cortese et al. In 2014, basically looking at the Tully Fisher, and I apologize, it's not VC, it's VROT. I know better. But and then we have the Faber-Jackson relation, and we can see that the different galaxy morphologies with the different symbol colors and symbol types lie very differently in these parameter spaces. However, using this parameter, the SK, and fixing K to be 0.5, this work was able to put all the galaxies of all the morphologies on the same scaling relations. Now, that doesn't mean that all galaxies are scaled versions of each other, if you like, but that does show some self-similarities that may be interesting to try and explain. Okay, so another very important diagnostic tool for stellar kinematics has been the spin ellipticity diagram. This is very much a descendant of the so-called anisotropy diagram that basically came up in the 70s and 80s. In even as early as the 80s, it was pretty clear already that a lot of the galaxies had a lot of rotational support, including elliptical galaxies, which might have been surprising at the time, but there is still, especially at very high masses, a significant fraction of very slow rotating galaxies, even at the time. So this is V over sigma. Now, with the advent of integral field spectroscopy and the Sauron survey, a new parameter called the spin parameter was defined. It's also similarly to V over sigma, is basically showing the rotational support over the pressure support. And so galaxies that are high in this diagram are more rotationally supported than their counterparts lower here. And just looking at within the Sauron survey, just the distribution of this lambda R parameter, there were two distinct bumps, if you like, in the histogram, with a clear family here of very slow rotating galaxies. So these were deemed slow and fast rotator families. So this is a thread that goes through a lot of these stellar kinematics community. And in the same way that we have the morphology density relation, we also have a kinematic morphology density relation. And I wish to emphasize at this point that the kinematic morphology and morphologies do not correspond as a one-to-one. Now, we love dichotomies in astronomy. We love to talk about blue ones and red ones and cores versus cusps and so forth. But I think in this case, it's important to emphasize that one of the findings of the stellar kinematics research is that, in fact, the two families of all of these different ways to look at two families don't always correspond. And so in this case, anyway, in this case, it does seem to have a hold in the sense that slow rotators tend to be located in the center of the most massive overdensities. This is work here using the SAMI survey, and we can see that even so, there are galaxies that don't seem to follow this pattern, obviously. And in Brough et al., especially in this paper and other papers subsequently, it was shown that the main driver of this kinematic morphology density relation was in fact mass. And the reason why slow rotators tended to find their way down these deep potential wells was because that's also where you find the most massive galaxies. Okay, and so this, with these large surveys now coming online, this is Manga's version of the spin ellipticity diagram. We can see that this parameter space has really filled up. And I'm showing here just another example which combines multiple surveys that was given in a review by Michele Capellari in 2016. And one thing I wanted to show was that the gap between fast and slow rotators isn't as obvious once you fill up that space. And the methods for dividing fast and slow rotators has also evolved over the years. And one such method that was recently published just late last year is to use Gaussian mixture models to try and identify statistically the most probable fast and slow rotators. So this is what these PFR, probabilistic fast rotator, PSR, probabilistic slow rotators. And we can see that they occupy different spaces, but that they overlap in even the stellar mass and lambda space, but also in lambda ellipticity space. So there is significant overlap between the two families, which means it's hard to see if it's really a dichotomy and if there's really a gap between those two families. But the Gaussian mixture modeling strongly indicates that two populations are favored over one. So this is a sort of a tick the dichotomy argument. However, I think we need to try and think about whether is it a dichotomy or perhaps is it a mixture of components, and then depending on how the galaxies are mixed, you get a different lambda RE value, for example. So this is work by Tabor et al. In 2019, where they've used, again, kinematic bulge disk decomposition to basically plot the bulges and disks separately in this space, and really clearly shows that the bulges, even in galaxies that can have a disk as well, tend to really occupy the slow rotator part of this parameter space, whereas the disks are really where you'd expect the fast rotators to be. So what do we have? Are galaxies like platypuses, so sort of hybrids with disks and bulges, or are they more like really a true dichotomy, ducks and otters? Perhaps another point of evidence that we may put towards this, or something to consider while we try and think about how to think about these different galaxy families and perhaps different components in galaxies, is that even two components, bulges and disks, may not even be enough to try and explain all that we're seeing. And so here, this is echoing some of what Adriano Porci showed in his talk, but we've got, this is a paper by Ling Zhu in 2017, and this is the Caliph galaxies and Schwarzschild dynamical modeling of the Caliph galaxies. And here they're ordered as a function of mass, with the lowest mass on the left and the highest mass on the right. And we have circularity, which is, it's explained better in Adriano's talk, but basically here I've given, and also they're giving some explanations of what these different orbits mean. But what we see clearly is that in most galaxies, there's a clear hot component, or a pressure supported component, if you like. And then in also most galaxies, there's also cold orbits and a clear population of cold orbits. But there's also a very significant warm component in many galaxies. So maybe it's the case that we have a bulge, a cold disk, a thin disk, a thick disk, and then we've got even this was for me quite a surprise, that there's 9% of orbits in Caliph galaxies are counter-rotating to the main body of to the other rotations. So counter-rotating stars are not that rare, or as rare as I personally thought they were. And again, we can see that it's at the very high mass that we start seeing this cold orbits disappearing more and more in favor of more hot and pressure supports. Okay, so now we've discussed this, let's try and go beyond and see how we can push this further to try and better understand. Oh, thank you. Right, so we've got here, this is just an example of using dynamical kinematic tracers to try and push the boundaries out. And we can see here in the inner parts, this is what Kokato et al. In 2009, the inner parts are showing the Sauron field of view, and then using planetary nebulae in the outskirts, basically reconstituting the maps statistically, they're able to show that these lambda curve as a function of radius can change significantly in the outskirts. And again, to try and understand the impossibly faint substructures in galaxies, we used dynamical tracers, so in this case, globular clusters and planetary nebulae, to try and model the infall of a satellite galaxy. And we're able to find two potential models and also identify the nucleus of the infalling satellite. So there's a lot of physics to be done with these dynamical tracers. And then trying to push not only out within a single system, but also out in redshift to try and understand evolution of galaxies. I think we heard yesterday about the legacy survey, and I think this is really quite pioneering work in this case, at least for definitely for stellar kinematics. And what they are showing very clearly here is that the rotational support in galaxies, when you compare the legacy survey, so at redshift 0.8, roughly 8 billion years ago, to the Caliph survey in local galaxies, is that galaxies used to have twice the rotational support in the past as they have today. So there's been a strong dynamical evolution in the stellar kinematics in the last 8 billion years or so. And the best way to probe this is to look at intermediate redshift, where we can still have a good signal to noise and a good data set. And so that's exactly what we've proposed to do with the MAGPIE survey. It's a new survey. We're going to look at a total of roughly 150 galaxies at redshift 0.3, so roughly 4 billion years ago, right bang in the middle of where we think that this dynamical evolution is important. And this is just an example, couple of stellar kinematic maps. And please stay tuned for more results from the MAGPIE survey in future years. In parallel to that, we've also had a massive flurry of action happening on the theory side to try and match exactly the observations that we see using the IFU survey, so that we can compare apples with apples. So I've heard this a lot in this conference already. It's only day 2. Apples with apples are very important. And so I just wanted to point out that there's this tool that is publicly available that basically uses particle data from theoretical simulations to transform them into kinematic maps in this case. So what we can then do is we can measure the same parameters that we do, in this case, V over sigma, ellipticity, for the simulations as we do for observations. That helps us to do 2 things: see where and how the simulations succeed and fail, and try and understand how to better improve the physics. And as a second point, if you have an observation, to try and find galaxies in the simulations that have similar properties, that we can then try and understand the range of scenarios that can explain these galaxies. So what's the outlook? I'm running out of puff. This is where to from here. So I think we're moving now away from phenomenological, and I can never say this word, and taxonomic studies into trying to understand really the physics, and we have now all the tools to do that. And it's also very clear that there's a real benefit for more holistic approaches to studying galaxy formation and evolution. There's a need to start collaborating across fields that have otherwise been fairly siloed. So in this case, I'm going to name things like the radio with the optical. And there's been, some forays into that, but I'd like to see personally much more consolidated approaches to try and understand galaxy formation between the different fields, high and low redshift simulations, and then even those that do detailed photometric decompositions. And I just show here a plot that Adrian already showed in his talk, because I thought it is such a great example of these multidisciplinary approaches, where here there's ionized gas data, there's the stellar populations, the stellar kinematics, there's local and high redshift, and so forth. So I think this is really quite a profound result. Okay, this is my last slide, and I've got a long laundry list here at the bottom of things I didn't have time to cover that I wish I had covered. So it is a huge field, but I just wanted to sort of re-emphasize the points that I've already made before. So I'll just leave my points up here, and I might wrap up here. Thank you.